Any high school chemistry classroom features this list of 118 known elements. For most students, it looks like a chaotic wall of data to be memorized for an exam. This grid functions as a strict coordinate system, mapping the electronic structure of every atom in the universe. Every horizontal row and vertical column dictates an element's physical state, its density, and its level of chemical reactivity. By learning to read these coordinates, we can look at any element on the map and predict its behavior instantly. The blocky, irregular shape of the table is a visual translation of how electrons occupy space. We can begin at the bottom legend, which classifies every element by its state of matter and general properties. Liquids are an extreme rarity. Only two elements, mercury and bromine, exist as liquids at room temperature. The vast majority of the table is comprised of solids. There is a clear geographical divide across the board. Metals occupy the left and center, while nonmetals are clustered on the far right edge. The border region between them contains the metalloids, elements like silicon that possess properties of both groups. These atomic structures cleanly segregate the physical reality of our universe, separating heavy, conductive solids from completely invisible gases. The horizontal axis of the map consists of 7 rows called periods. Elements in period 1 have only one main energy shell, the K shell, to hold their electrons. As we move down from period 2 to period 7, every new row indicates that a completely new outer electron shell has been added to the atom. The table lists this growth numerically. In period 4, potassium shows a stack of numbers, 2, 8, 8, and 1. These stacked digits represent the specific distribution of electrons across each of the 4 shells. Every period provides a visual record of an atom's energy levels expanding outward. Shifting to the vertical axis, we find groups 1 through 18. Every element in a vertical column shares the exact same number of valence electrons, which are the electrons located in the outermost shell. Group 1, the alkali metals, includes elements from lithium to francium. Their configuration numbers all end in a 1. This single outer electron makes these metals highly reactive, as they are prone to shedding that electron to reach a stable state. Group 2 elements, the alkaline earth metals, possess 2 outer electrons. They remain reactive, but require more energy to interact compared to Group 1. A vertical column identifies an element's chemical personality, determining how it bonds with other atoms. Moving across the center, we reach the P block in groups 13 through 16. This zone contains a varied mix of metals, nonmetals, and gases. This area provides the essential components for life, including solid carbon and gaseous oxygen. Group 17, the halogens, contains elements with 7 outer electrons. Because they require exactly 1 more electron to complete their shell, they are aggressive chemical partners for Group 1 metals. This interaction allows sodium and chlorine to bond and form salt. Group 18 contains the noble gases. In this column, every element's outer shell is completely full. With full shells, these elements have no need to react. They remain stable and chemically inert. Chemical reactions throughout the universe are driven by atoms attempting to reach the stable configuration found in Group 18. The large central block we bypassed contains the transition metals, which are the hard, durable elements used to form complex ions. At the very bottom, 2 rows called the lanthanoids and actinoids appear to float separately from the main grid. These rows actually belong inside periods 6 and 7, immediately following Group 3. If we inserted them into their proper mathematical sequence, the table would become too wide to display easily. We separate them simply to fit the map onto a standard page. This bottom row includes heavy, radioactive elements like uranium and plutonium. The layout of this entire map is dictated by the precise order in which electrons fill their energy levels. The primary value of the periodic table lies in its capacity for prediction. On the bottom right, the heaviest elements show mass numbers inside parentheses, such as rutherfordium at 267. These parentheses indicate that the element is so radioactive and unstable that we can only measure the mass of its longest-lived isotope. Even if an element exists for only a fraction of a second in a lab, its coordinates on the grid reveal exactly how it behaves. From reactive gases like hydrogen to dense solids like uranium, every physical property is a result of an element's position on this map. Periods and groups dictate how atoms assemble into the physical world. the periodic table remains the foundational blueprint for all physical matter in our universe.